The CLO for this lesson is that students will be able to compare, in writing, key features of quadratic situations using graphs, tables, equations, and situations, as well as the following language: transition words, quadratic, x-intercept, y-intercept, vertex, and then horizontal stretch/shrink. So if I start with our vocabulary, so for the first 4 words, I'm going to skip asking you about them. We know what they are. Quadratics are equations where the base exponent is 2 and it makes that parabola shape, the U shape. X-intercepts, they cross the x-axis, therefore y is 0. For y-intercepts, it's where they cross the y-axis, therefore x has to be 0. And then the vertex is either the top or bottom of that parabola, which ends up being the minimum or the maximum y value. The sort of new one that we learned in the last lesson is another key feature is if there's an a in front, of the equation, then it's going to either stretch the graph or shrink the graph. And I'm going to show you one more time a picture of that. So if the normal graph is x squared, and it looks like that. And I'm going to take x squared again in blue, so it's in the same place right now. But if I put a number in front, it changes it. And so the vertex is still in the same spot. It's still right there as 0, 0 right now. But what happened to this graph is that it shrunk in. Well, depending on how you think about it. Because if you think horizontally, so side to side, it's like you took the red graph and you pushed it in, so you're shrinking it together, like a push. And so that would be called a horizontal shrink. However, some people like to talk about it vertically. So some people will call it the horizontal stretch/shrink, and some will call it the vertical stretch/shrink. And it doesn't matter, because it means the same thing. It's still talking about the a in front, whether or not they use this word or this word. However, just so you quickly understand it, vertical is up and down. So you're not shrinking it up and down. If you think about it, it's like if they took it down here and grabbed over here. It's kind of like they pulled it up. Like it gets taller faster. After one here on this graph, one here on the red graph is only at 1. But it's taller on the blue one, because if I'm at 1 on the blue one and I go up, it's at 3 because of that 3 in front. So because I'm multiplying it, it's getting multiplied faster. It's going up faster than if there's not a number in front. So it'd be called a vertical stretch because vertically it's going up quicker. But horizontally, if you think side to side, it's shrinking because it's like it's pushing the red one in. If I put a fraction here, now the blue one's fatter than the red one. It got wider. So if you're thinking horizontally, it's like they grabbed the red one and pulled it sideways, pulled it out. So this one would be called a horizontal stretch because it's stretching side to side. But vertically, it'd be a vertical shrink because it's like it's pushing it down. If you look at 1 on the original, the red one, it's at 1. But then at 1 on the blue one, it's less than that. It's about half. So that's the a value in front, the horizontal stretch/shrink, or vertical, depending on whatever they say. And it's the a value in front of the equation that either makes the graph thinner or fatter. And that's for the horizontal way to think about it. The vertical way to think about it is taller or shorter. That's what it does to the graph. All right, so we've talked about all of them on a graph, like where it crosses the x-axis, where the graph crosses, where the graph crosses. So we talked about it on a graph. Oh, and here even, it's making the graph taller or shorter. We've talked about it in a table sort of are these 3 for the table. We haven't talked about this one in a table because you can't see it in a table. You have to solve for it. But we can see it in an equation really easy because it's the a in front. Where these 3 with the equations, these are the ones you have to solve for equations. So we know almost all of them, either how to solve for them or where to find them because of the definitions. But I haven't exactly called out yet where they all show up in situations. They've shown up in the challenge questions, but I haven't put them into note form yet. So for situations, it's important to remember that x, when we talk about the x value, it's talking about time usually. Not always, but usually x is like how much time has gone by. It could also be like distance, like how far away something is. Sometimes it's how many times you do blank. So like if you're going trick-or-treating, for example, and you're counting how much candy you have, the X is how many houses you go to. So it's how many times you go to a house. Or it could be how many times you go to work or how many times you go to the store. So basically, the important thing to remember about it is that it's the independent variable, which means it exists by itself. Time just goes by. Distance, like when you're moving away from something, that just happens. It kind of like it exists by itself. It's independent. Versus the y value. Y value is usually the amount. So when I say amount, I mean things like how much money you have, how much weight you carry, how tall you are, like how much height you have. In the Halloween example, it would be like how much candy you have, the amount of candy. So anytime you can say the amount of blank, that is the dependent variable. It's the y. And the reason why it's dependent is because it depends on the x. So like how much money you have depends on how much time you've worked. The height of something might depend on how far away it is from something else, like its distance from something. Here's the thing about distance. I'm going to italicize it and make it italic, but it's because it can also be the y. It can also be the amount. I'm going to put it here next to height. Because if you're thinking about like you're walking somewhere, then the distance away you are from your starting point depends on how much time has passed. So in that case, when it's talking about distance and time, like minutes or seconds or hours, then in that case, distance would be the y. But when it's a situation that has distance with something else, like height, height's a common one with distance. Like it's common to throw a ball, and how far away it is from where you threw it will determine how tall it is. Because over time, it's going to go higher up and then it'll come back down. So in that case, the height of the ball depends on the distance of how far away it is from you. So that situation comes up to a lot. So knowing this in situations, x-intercepts, remember, is when y equals 0. So if y is 0, y, the amount, is 0. Meaning in this case, it's things like when you have nothing, it's an x-intercept, like if you have no money. If you have no height, like you're on the ground, you're at the 0 for the height. If it's one about distance and time, it's when you have no distance away from your starting points. It's when you have absolutely nothing, because it's the amount being y. For y-intercepts, remember, it's when x equals 0. So x in a situation is usually time or distance, but no matter what, it's how much you have, because the y-intercept, there's a y value, so how much you have. Whatever that y-intercept, like for example, if it's 0, 7, that means you have 7 right now. But the 0 is no time has passed. So how much you have when no time has passed. So this is at the very beginning. Not a second has gone by. No distance have gone by. You haven't gone to a single house when you're trick-or-treating. So before you even begin. So another thing, a way they talk about it is your starting amounts. So when you start, before any time has passed, how much do you start with? That's your y-intercept. The vertex, remember, is the minimum or maximum y value. So it's about the y value. And remember, the y value is how much you have. And so the word minimum means the smallest, and the word maximum means the biggest. So the vertex is when you have the most or least amount of whatever it is, whatever your y is. And finally, the horizontal / vertical stretch / shrink of a situation is a bit harder to identify. But basically, it tells you, remember, it either makes it shoot up really fast and stretch up to the sky. So it either the y amount, because that's the y that's going up. The y, the amounts you have, either grows quicker or slower, depending on the A. So sometimes the A will make it grow up really, really fast in comparison to what it would be without that A, or sometimes it makes it slow down and take more time to go up. Like this one, for example, the red one, it's going up much quicker. Like for example, after 2, it's already at 4. And the blue one's only down here at 2. And then by x being 5, if I go up, this blue one's only at like 12 point something, 12.5. But this red one is all the way up here at 25. And 25 is a lot more than 12. So this one's just shooting up a lot quicker. So there's this expectation that they can give you this real life example and give you a bunch of other representations like tables, graphs, equations, and that you can pull out all of the key features and understand all of the key features in terms of the situation they give you. And then compare them to each other and make judgments based on that situation. So I have one big example of how we're going to do that, and the worksheet has another example of it as well. So this is a real life example for me because I went to South Africa and I studied abroad, and I went on this swing ride. It was a lot of fun. It's called the Big Rush, and it's a swing company that's located in South Africa, and it allows you to pay some money to jump off of the FIFA World Cup stadium. So just so that you understand what's going on, I found this video this guy made of it. So this is, you have to get dressed up in this thing because you're gonna connect to it to keep you safe. And then you have to walk up all these stairs. Like there's like 250 stairs or something. And this is the FIFA World Cup Stadium, and they attach you to the swing. Yeah. And you get to jump off, and you free fall for a while until that rope free fall. 3, 2, 1. Okay. And eventually the rope snaps. This is me doing it. This is my video from South Africa. It's a worse quality. But you can see the shape it's going to make. Watch the shape the swing makes. It's going to be a quadratic. See, down, and I U out, because it's a swing. And it goes back up to the other side. And then it's going to go back and forth. And eventually I'll settle at the bottom. Right at the bottom of the quadratic, which is where the vertex is where I'll settle, where my butt will be at the lowest point. Lowest point right there. Boop. And then I'm going back up. And eventually it settles and they start to raise you back up to the top. Yeah, I cut that part, whatever. So yeah, that's the concept of the swing. So it makes a quadratic shape. And the employees at the company are trying to determine what formula they need to program that swing for to ensure that the ride is super fun, but also safe. The machine is set to think that the platform that you stand on right before you jump at is at a distance of 0, because the machine's right there. So I'm 0 feet away from it when I'm standing right before I jump. And the height is going to be 0. So it says where the man in red is standing in the picture below. This is the picture. So right here is 0. And jump off, and you're going to go down into the negatives. So that ground's down there in the negatives. And then right when they go back up to the other side, it would be right at the same height at 0. So this whole graph's down in the negatives in this situation. So here's what we know. If right here is 0, the other end of the stadium is 100 feet away. So imagine right over here at the other end, if there was another platform there at the exact same height. Right here is height 0, but it's 100 feet away over there at the other end. And the floor is 80 feet below the jump off point. However, it's important to note that the weight of the person can make this swing sink up to 10 whole feet. So you can't like program it to go 80 feet down in case the person makes it sink a little bit. So 3 different employees have turned in different representations of plans they think they could work for this swing machine. So here are the representations, and we have to analyze them and compare the key features. So to do that, so that we can tell them which solution we should use. So in order to do that, we have to pull out all of the key features. So these are the 4 key features we have to look at. In order to get them, it depends on what form it's in, and then it's the notes, one of the different lessons you've learned in the past. So what form is this in? It's basically in factored form. You do need the +0 to be perfect factored form, but you don't have to have it because it's just nothing. And in order to get the x-intercepts, what do? You use the 0 product property by setting each one equal to 0 and solving. So if I were to do x, the first parentheses, which is just x, equals 0, there's no need to solve it. It's solved for. X is 0. So one of the x-intercepts is 0, and then comma 0. And the other one, what I make x minus 100 equals 0. How do I solve that for x? I add the 100 over to find out that x is going to be 100. So my other x-intercept is 100, comma 0. Bold her original equation. All right. For the y-intercept, how do I find it? I take my equation and I plug in 0. So if I do 0 minus 100, I get negative 100. And then 0 times negative 100 just equals 0. For my y-intercept, when I plugged in 0, I got out 0. That's my y-intercept. My vertex, how do I find my vertex? Well, it's right in the middle of my 2 x-intercepts, and what's between 0 and 100? Remember to figure it out. You can add them together, which equals 100, and then divide it by 2, which equals 50, because 50 is right in the middle of them. So that's how you get the x value. To get the y value, you plug 50 into here. If I do that math, I put 50 into that x and 50 into that x. 50 minus 100 is negative 50, and 50 times negative 50 is negative 2,500. So when I plug in 50, I get out 2,500. You could always use a calculator for that. So that's my vertex. And what's my horizontal stretch / shrink? Remember, it's the A in front. Is there a number right here right now? Well, secretly, it's the invisible 1. So A is this invisible 1. 1 is the normal one. It has no stretch/shrink. So it's not getting changed at all when it comes to the horizontal stretch/shrink. A is just 1. For the table, if I pull out all 4, the x-intercepts are what? Well, there's this 0, 0, and this 120, 0. Y-intercept for the table. This is 0, 0. Where's your vertex? Remember to get this one, you look at the y's. So this is 0, then it goes down to negative 52.5. Then it goes down to negative 70. Then it goes back up to only negative 52.5. Then all the way back up to 0. So the vertex is right here at negative 70, and that's the y. The whole point is at 60, when x is 60. The y is negative 70. For tables, in order to figure out if they have a horizontal stretch/shrink, you actually have to determine this, you have to figure out the equation. So to quickly remember the last lesson, you can take the two x-intercepts, for example, and put them into factored form. So with the 0, the opposite of 0 is just 0. So you would have x plus 0. And the opposite of 120 is negative 120. Then you put an a in front, and you see if there is an a value by plugging in any of the other points. So let's do the vertex, the 60, negative 70. So that means it's going to equal negative 70 if the x's were 60. So 60 plus 0 is just 60. 60 minus 120 is negative 60. When I do negative 60 times positive 60, I get negative 3,600. So I have to divide that over to the other side. So I have negative 70 getting divided by negative 3,600. That's going to be my A. If I do negative 70 divided by negative 3,600, I get this decimal point, 0.019444444. So my A is 0.019. You can just put the first 3. So that's the A we found, 0.019. So what is this going to do to my graph? Is it going to stretch it or shrink it? Well, let's look at it in decimals. So I had just the x plus 0 and the x minus 120. That's the original without the a. And then if I put the a in front, the 0.019, what happened between the purple graph to the black graph? Let's think vertically up and down. To go from here to here. Am I vertically shrinking down, or am I vertically stretching more? To go from purple to the black. Technically, vertically, I'm going here and I'm shrinking it up. I'm pulling it up. So it's a shrink up. So decimals, things less than 1, shrink your graph because you're multiplying it by something less than 1. And anytime you're multiplying, like if you're doubling something, that's making it more because you're timesing it by 2. So like timesing it by more than 1 would stretch it out. But anytime you multiply by a decimal, you get less. Like if I have 5 and I'm multiplying by a decimal like 0.3, look, that's less. 1.5 is less. If I multiply by 0.7, still 3.5 is less than my original 5. So anytime you take a number and times it by something less than 1, then it's going to be smaller. But once you hit 1, then it becomes 5. then anything more than 1, even if it's 1.2, that's still more than 5. It's still going up. So A values. If it is less than 1, you are shrinking the Y value. If it is more than 1, you are stretching it out. So in this case, since it's less than 1, it is shrinking. Go back up to the situation piece. It means it's growing slower. If it's growing slower, it's a shrink. Versus if it's going quicker, if it's going faster, it's stretching. So in this case, the graph is getting shorter or shrinking. All right, and the last representation is a graph. So in this graph, where are my x-intercepts? There's one at 0, 0, and there's one at 100, 0. There's my y-intercept. Crossing the y-axis right here at 0, 0 as well. And where's my vertex? Humping right here at 50, -70. And again, to figure out the A, I have to do the equation. This time, why don't I do it starting in vertex form, since I did factored form with the x-intercepts last time. In vertex form, you do x, and then you do opposite of what the x value next to that. So instead of 50, it's -50. You square the parentheses, and then the k is just that last number, so it's going to be -70. And then to figure out if there is an A value in front, you go ahead and plug in a point. I'm going to go ahead and use this x-intercept, 100, 0. So when I plug in 100, I should get out an answer of 0. 100 minus 50 is -50. And then -50 times -50 will become positive 2,500. And to solve for that A, I first have to add this -70 over. So 0 plus 70 is 70. And then finally, I divide that 2,500 away. And my new equation is going to be 70 divided by the 2,500. And that's going to be my A. And so if I throw that in a calculator, I get 0.028. So here A is 0.028. So jumping back to our A rules, if it's less than 1, you're shrinking the y's. If it's more than 1, you're stretching. So am I shrinking or stretching? It's less than 1, so I'm graph is shrinking or getting shorter. So now for all of them, I have figured out the 4 key features. So I had to do that first in order to be able to compare them to each other. So a comparison does things like relates it back to the situation. So I had f of x, j of x, and g of x. So I grabbed the key features for the 3 functions, and I put them all side by side. And now we're going to relate them back to the situation a little bit while we compare them to each other. So I'm going to actually just start with comparing the x-intercepts. All 3 have 0, 0 as an x-intercept. So, does this make sense in terms of the situation? So let's talk about what that means. 0 in my situation of the swing means that my distance from the machine itself is 0 and that the height's 0 at that point. So if I'm standing on the ledge, my distance, I haven't jumped yet, and it's saying my height's at 0. Does that make sense for the situation to have these as x-intercepts? Yeah, it needs them. It's one of the first rules in the thing. The machine is set to think that the platform you stand on before you jump is at a distance of 0 and a height of 0. They tell you that in the problem. So it's a good thing that they all made sure to have that. So if I'm comparing them in terms of the situation, I would say this makes sense because, okay, so in this lesson, in the CLO, remember we're working on using transition words. And transition words are words we use to go from one thought to another. And when you're speaking or writing, it's important not to use the same transition words all the time. Like, for example, every single time if you use if then statements and you always say, if this, then this, if this, then this, that gets really boring. So you can start to switch it up a little bit by using transition words. So, transition words that are common in math is to say you'll say a sentence and then you can conclude something by saying therefore. Then that's how you know you're like summarizing what you just said. If you want to say something and then contradict it, you can say blah blah blah, but you could say blah blah blah. However, um, so like however is another way to say even though this is true, however, there's something else. You can say in comparison, 'cause that's a way to say, like, this is happening, blah, 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 but in comparison, this happens. The word and is a transition word. Like, there's this and there's this also is a transition word. If I think of more when I'm writing things out, I'll keep adding to this list. However, in this lesson, you're going to practice using as many transition words as possible when you explain things. So, if I'm talking about how all three have 0 as an x-intercept, I can say that this makes sense because is a transition word. Because the machine is at the jumping point and the height is 0. Um, let's keep looking at the x-intercepts though, because there was some differences. So this was a similarity, but now we're going to look at a difference. So this one has 100, 0. This one has 120, 0. And then this one has 100, 0. So f of x and g of x have the same second x-intercept as a transition word because this is about a similarity. Now I'm going to change my thoughts up and start thinking about their differences. So if I want to use a transition word to signal this, I can say, however, only f of x and g of x have the same second x-intercept at 100, 0. J of x is further away at 120, 0. So in terms of the situation, 100, the x is the distance, how far away from the jumping point you are. And if I go back up to my original problem, it says the other end of the stadium is 100 feet away. So if it's only 100 feet away, how is person J thinking that they're going to get to go all the way to 120? That's not where it's at. It's too far away, so when the swing comes up at 100, it's gonna hit the wall on the other side. It can't go all the way to 120. So that causes a problem. J won't work. It's too far away. The other end of the stadium is only 100 feet away. Because of that, and then instead of using because I've already used because right here, so I'm gonna try to use a different one. So a different word for because, I can also use therefore. The end of the stadium is only 100 feet away. Therefore, J of x will not work. The x-intercept is too far away. All right, so I've compared and analyzed the x-intercepts for them so far. Now I'll do the y-intercepts. So if I compare the y-intercepts, this one's at 0, 0, this one's at 0, 0, and this one's at 0, 0. So they're all three the same. All three have 0, 0 as the y-intercept. And this makes sense. For the same reason as the x-intercept, because the machine is at the jumping point, so you're 0 distance away, and the height is 0. So at the start of time, before you jump, you are no feet beneath the machine because you're where the machine's at. You haven't jumped down yet. Now I'm going to compare the vertex for all three of them. This one is at 50, and then I accidentally wrote 2,500, but it was definitely negative 2,500 because you're going down. When I put it up here and we did the math, for some reason I forgot to put the negative on it. So go back and change that in your notes. This one is at 60, negative 70, and this one's at 50, negative 70. So let's start with something that's the same. What's the same about any of them? Well, there's two things that are the same. In f of x, the vertex is at 50, and in g of x, the vertex is at 50. But in j of x, it's at 60. So that's a difference about the x value. So let's write that down so far. F of x and g of x have the x value for the vertex at 50. J of x has it at 60. So this is one similarity and one difference about the x value. And if you notice, it matches the x-intercept differences, where f and g are very similar, and j is the weird one. But remember, j was also the wrong one. And if you remember, for vertex, it's always in the middle of your two x-intercepts. So for the two that had the x-intercept at 100, like it should be, the middle of 0 and 100 is 50. So these two have the two correct x-intercepts, which means the vertex will be at the right place. But since this one has the wrong x-intercept, then it's going to have the wrong vertex in the middle too, because the middle between 0 and 120 is at 60. So this is because j of x has the wrong x-intercepts, so the vertex is wrong too. It's not the right one for our situation. Like we've determined J is a no-no. So because we've determined J is a no-no, we don't really have to talk about it anymore. So between the f of x and the g of x, who we know have the right x-intercepts and they have the right y-intercepts, who has the right vertex? Can it go down 2,500 feet or should it only go down to 70 feet? It definitely should only go down to 70 feet because if you remember at the top, the ground, the floor is 80 feet below the jump off point, but it doesn't go to 80 because the weight of the person jumping can make this swing sink up to 10 whole feet. So to account for that 10, 80 minus 10 is 70. So it can only go down 70 feet. So it's going to have to be this g of x. Because f of x goes down a lot more, but that's too far. If you look, the j of x also goes down to negative 70. So the person who made this had the right vertex. So they knew where to start and they knew where the vertex needed to be. The person who made the table, they just didn't understand the x-intercept was too far away for this one to work out. So even though j of x has the wrong x-intercept, so the vertex is wrong too, that doesn't mean that the y value of the vertex was wrong. They knew it could only go down 70 feet. So a transition word I can use for this would be however. J of x knew that the y value for the vertex had to be negative 70 because the swing can only go down 70 feet. This is similar to g of x, who also has the y value at negative 7b. Next, I want to use the word however so that I can explain the f of x part and how it's different, but I already used the word however. So instead, I'm going to do comma but, because but is another way to contradict something. So this is similar to g of x, who has the value at negative 70, but f of x has a much larger x-intercept at negative 2,500. This is too far down. They'd hit the ground in the swing. The ground is only 80 feet beneath the ground. This is way more than that 80. So it'd be way too far down. Way, way, way too negative. Because of that, therefore, the f of x, it's wrong. You can't use this f of x one. So finally, the last one to compare are the horizontal or vertical stretch shrinks. And so if we look at that, f of x had a being 1, which was normal. J of x, they made it shrink. G of x, they made it shrink. So j of x and g of x both made it shrink. So g of x and j of x made their graphs shrink, a bit shorter. And why'd they do that? Well, what else did g of x and j of x get right together? Both of them. If you go back through the work, you can see they both got that negative 70 right. Remember, they also had this vertex being correct. So they made their graph shrink. When this one didn't make it shrink, look how far down the graph went. It went way too far down. So the horizontal shrink made it shrink so that the vertex wouldn't make them hit the floor. So this is because they needed to make sure the person didn't go too far down and hit the floor. So after comparing all of them to each other and all of their key features, what was the same, what was different, why, what that meant, I was able to figure out that these two were bad representations, that I'd need to use the g of the x. So whose equation should get used? G of x is the best one. And I don't have to explain why right here because I explained it all up here. But I could have, if I wanted to, take in my end statements, like the therefore the j of x will not work for the x-intercepts too far away. That could be a part of my reason why here. For the next one where I say, this is too far down, they'd hit the ground, therefore f of x is wrong. The comparison can just say that it's larger. And then down here, I could say this is why g of x is the best one. And then I can say g of x has everything right. I wouldn't start a sentence with therefore. I'd just say g of x will not work. X-intercept is too far away. When I say this is too far down, we're talking about the vertex. So f of x is wrong. The vertex goes too far down. They'd hit the ground. And then g of x has everything right. So if they expected you to explain, if they said, explain your answer, this is the part of the comparison that you'd use to explain your answer. So this one says, Jen realized the mistake she made in her equation after looking at the g of x graph. Her new equation she presented is this. And it wants to know why the equation's correct. There are quite a few ways you could do it. You could take it and you could prove the x-intercept, y-intercept, and vertex, and you'd get all the right ones, and then you explain why it's correct. You could graph it and say after graphed, when you look on the graph, you can see where the x-intercepts are, the y-intercepts, and the vertex, and explain why they are all correct in terms of the situation. But at the end of the day, no matter how you do it, you would say something along the lines of either after solving for the key features or after graphing the equations, you can see however you choose to prove it. And you would actually have to prove it. You'd either have to graph it or you'd have to do the math. And then you would say the x-intercepts are 0, 0 and 100, 0. This is because the machine is at height 0 and the other end of the stadium is 100 feet away. The y-intercept is 0, 0 because before you jump, you are no feet below the machine. Or on the same level as it. And then finally, the vertex is at 50, negative 70, because in the middle of the stadium, at 50 feet away, you can allow the swing to go down 70 feet. You can't go the full 80 feet because you need to leave 10 feet in case the swing sinks. And that's why you'd explain the equations correct in terms of the situation. after you either solved it for its key features or graphed the equation. All right. So go ahead and use transition words as well as the vocabulary to explain what you learned how to do in this lesson.